This video is going to give an overview of the randomized control trial design, and it's a bigger topic than I thought it was going to be. When I originally created this slide deck, it ended up being like over 100 slides, so I ended up taking certain topics and putting them in other videos. So in this video, we're not going to talk about block randomization, stratified randomization, anything with compliance, or factorial designs, but they will be covered in another video I'm hoping to get to after this. So in a typical randomized control trial setting, let's say we're looking at whether a cancer treatment is better, like a new cancer treatment is better than the existing cancer treatment. So we get this group of people that all have the same cancer type and the same cancer severity, so they're at the same stage, basically, in their disease progression. And then we have our new cancer treatment and our standard one, and we randomly assign people in this group, either through assigning them a number and doing a random number generator or like some kind of software. But basically, and random also doesn't mean haphazard, like where it's like kind of randomly allocating. It's a formally random process usually. And what that achieves is these two groups are as similar as possible, except for the fact that one group got the standard treatment and one group got the new treatment. So then we follow them forward. Typically it's a prospective design in a randomized control trial like this. Say we're following them 5 years. And then if the outcome is death or survival, anyone who's red here means that they died, where if they're the color they remained, it just means that like they are someone who survived in the new treatment group if they're blue, and someone who survived in the standard treatment group if they're colored black. And what this basically lets us figure out is if people who were given the new treatment on average lived long, like had greater survival after 5 years. And they didn't need to die on the 5th year. They could have died anytime during the follow-up, and that's what these red people represent. And just kind of, without even analyzing it, you can kind of see that there's fewer people that died out of the, like, basically the same number of people in the new treatment group. So that would be an indication, if we analyze it formally, that maybe this new treatment was protective. And the fact that we randomly assign treatment tells us that it's the treatment that led to a differential mortality rate, basically. You'll notice that I had a new cancer treatment and a standard, but something some of you might be more familiar with is a placebo as the other group, and that's only suitable in certain situations. So there's this concept in randomized control trials called equipoise, and that's that you can't knowingly give one of the groups an inferior treatment. So when it's a disease that has no accepted treatment, then a placebo can be used because we don't have any evidence that this new treatment is any better than the placebo. So by giving them the placebo, basically we're not knowingly giving anyone an inferior treatment because there's no superior treatment, basically. But when a standard accepted treatment exists and we're trying to see if this new one is better, we can't give them a placebo because we already know that no treatment is worse than whatever we're currently doing. So you're not able to use a placebo in our example here because there is a standard treatment. Willingly not giving these people with cancer any treatment is not acceptable, so you have to give them the standard treatment. And also, in certain studies, there's periodic analysis of the evidence we have so far. You do it every couple of years if it's a long trial. And as soon as there's enough evidence that one treatment is better than the other, it's unethical to continue, basically, because all of a sudden you're violating equipoise. Once you have enough evidence to say that one treatment is better, you need to stop the study. And just while we're talking about ethics, there's another ethical idea that you need to get informed consent from every participant, usually before they even, like, it's basically the first interaction you have with the participant before you even measure anything. And consent is not the same as informed consent, because you need to be truthful with them about the study unless there is deception involved, which is common in psychology studies, where by telling them about it you're defeating the purpose. That's not nearly as common in epidemiology, but basically informed consent means they know what they're signing up for, in addition to the fact that they're willing to do it. So why do we randomize? Epidemiology is a largely observational discipline, but randomization is sometimes useful depending on what your question is. So the reason randomization is so respected is because it effectively controls both known and unknown confounders. So let's start with a known confounder. So if we're looking at treatment, like a new cancer treatment versus the standard and survival, and we think that age might be related to treatment and survival, let's think about why age might be related to the two. It'll help with visuals. So this is a situation where so people who are blue are 50 and over, so they're older people, and the people that are colored black are under 50. So in our standard treatment, it seems like we have more people over 50 than in the new treatment. And notice that this is an observational study. No one's being randomized right now. This is just the way things work in the real world, where doctors are making decisions based on what they think will be the most effective treatment for a patient. Doctors don't randomize treatment. They decide based on a variety of factors, one of which might be age here. So let's say people over 50 are viewed as frail, and this new treatment is considered aggressive, and they think that younger people will have a much better chance of benefiting from it than older people, because older people might be so frail that the new treatment might hurt them more than it helps them, basically. Another situation, this is one where the new treatment has a lot more people over 50. Also, you could use the same reasoning to say it might be better to have people over 50 applied to this new treatment, because they're often at a later stage of cancer, and they might require a more aggressive treatment, basically a Hail Mary pass. So in that way, age is related to what treatment they might receive, and age is obviously related to survival. That's intuitive to people, that the older you get, the more likely you are to die. So this is a classic confounder, because I just showed basically how age can be related to both treatment and survival. So how do we get around that? We have an uneven distribution of this confounder in the two groups, so they're not exchangeable. Ideally, we want to be able to say that these two groups are the same in every single way except for the treatment they got. So that lets us say that the treatment is the reason that they differed in mortality rate. Randomization basically breaks down because I told you, I have a whole video on confounding, but basically, to be a confounder needs to be related to both the treatment and the outcome. Randomization breaks the relationship between the confounder and the treatment or exposure. How we do that is we take our group and jumble it into one group, and then randomly allocate people through some formal randomization process to the two treatments. And usually you have way more people, so this is an example of it being like contrived, because we got perfectly 3 out of 20 in both groups, but on a large scale you're likely to get this. There's ways you can be more sure of that, like stratified and blocked randomization, or stratified randomization, and I'm going to talk about that in another video. Cluster randomization is another one where basically, so like a cluster is any group of people that, like for example, a household, and certain treatments are better to assign at the group level rather than picking one individual at a time to assign their treatment. So like a household, you might be able, like as far as like a family, you might be able to have an intervention, like some new dietary intervention, like a supplement, or basically just manipulating their diet in some way, that if it's like a family that eats together all the time, then that is a useful cluster to randomize. If we're randomizing a classroom, it might be some addition to the curriculum that aren't provided to other classrooms, where we see if they do better on some standardized test. Or something like water fluoridation, where like a town's water source, you can't individually assign members of the town if they're all getting the same water source, so you might treat a town as a cluster and basically assign water fluoridation to one and not another. Since clustering is happening here, clustering is a big issue that I'm going to do a video on, and it's basically when individuals in a cluster are more similar to each other because of factors that relate to, like, for example, classrooms. Like a clustering effect would be the teacher, or like if it's a household and they're all related, the genetics is something like an agent of clustering, basically. And cities, that people from a given city share a lot in common. So basically accounting for the effect of clustering is something you would need to do in the analysis. So with regular randomization, one person is assigned at a time, basically. So this person was taken out of the crowd, and this is like a oversimplification. It's more of a formal process, but this is basically what's happening. And then this person's being randomly assigned to one of the treatment groups, randomly assigned, and it's not ordered. Like this, just because it went there, it doesn't necessarily go back here. It happens in a random order, basically. And the reason that that could potentially be a problem is, let's just say you flipped a coin 100 times. You'd expect, like, the more times you flip a coin, the more likely it ends up being heads and tails an even number of times. But if you flip a coin like 100 times, it's possible you could get heads like 75 times. And the reason I bring that up is because you could end up with like 75 people in this group and 25 in this group, because every time we flip a coin to decide which direction they go, it's an independent event. So by chance, one group can be way bigger than the other. And I'm not going to talk about that in this video. That's something called blocking that is going to come up in another video. So with cluster randomization, the same way we were taking individuals and picking them out of the crowd, we take clusters, and they're the unit of randomization, where we pick a cluster out of the crowd, assign it, and everyone here gets that new treatment, whether it's a dietary measure in addition to the curriculum or whatever, and we do it again, and yeah, that's basically cluster randomization. So as far as visualizing randomized control data, it's usually a prospective thing, where let's just say these are the people getting the standard treatment, these are the people getting the new treatment. They're followed for 5 years, and when an event occurs, it's a dot. We're going to assume there's no lost follow-up, so basically when this blunted end would happen is if they get to the end of the 5 years and didn't die. So after year 1, someone in this group had the event, so if I'm continuing with the example from before, they died. In year 2, there's another event now in the treatment group, and you basically just continue until the end. And I'm going to show you how like this data can basically be tabulated. So for each observation, like that's observation 1, you have their treatment status, their number of years of follow-up, and whether they died, basically. So this first individual was in the standard treatment, they were followed for 4 years, and they died. For example, the second one, they were in the standard treatment, still the black line, followed for 5 years, and they didn't die. So basically what that tells us is after 5 years, you leave the study for one of two reasons. Either you survived or you died. So this is a dichotomous variable in that way that gives us all the information we need in only being represented as binary. So as far as analyzing this randomized control trial data, I have whole videos on time to event analysis. I recommend checking that out, or Poisson regression or logistic regression. Basically, there's lots of ways you can analyze this depending on what you're hoping to get out of the data. So Poisson regression is a way that you can get the rate ratio, so the rate of mortality in the new treatment group versus the rate of mortality in the standard treatment group. If you think the event is rare enough, you might be able to get away with logistic regression. If you have a binary rare outcome, you might be able to estimate relative risk. That's the risk in the new treatment group versus the risk of mortality in the standard. But even if it isn't rare, you could still do that, but it would be an odds ratio. And I guess probably one of the most common ones, especially for the scenario that I've described in this video, is survival analysis, where you're looking at the hazard, so I guess like the time to event, time to mortality in the two groups, and seeing if they differ. Specifically, we call it a hazard ratio, so like the ratio of the hazard in the new treatment group and the standard, but it essentially just estimates a relative risk or a rate ratio. A lot of people outside of epidemiology wouldn't understand what a hazard ratio is, but it can be interpreted very similarly to a relative risk. And yeah, that's basically how you would analyze randomized control data. It has some advantages, so it's very like I said, it's very powerful to control for both known and unknown confounders. I don't know if that came through in my example. I talked about age as a known confounder, but there's also like situations where like people like it so much because basically, like if you're talking to a doctor and trying to describe your results to them, and you say like, oh, I controlled for age, I controlled for this, I controlled for that, basically there's no way to refute the argument that someone could make that what if there's another confounder you didn't measure and you didn't control for it and it might be influencing the results. You don't know what you don't know, so it's impossible to really defend that. But randomization is so respected because it basically doesn't rely on you counting all of the confounders and coming up with every single confounder, because if you randomize, basically it ruins the relationship between the treatment and anything. Basically, it basically eliminates the relationship between the treatment and everything except mortality or whatever the outcome is, because that's the only thing that hasn't happened yet, and it's impossible for it to be related. But yeah, no, that's kind of more a philosophical argument that. But just, I guess, long story short, randomization is really it's good for controlling both known and unknown confounders, and very understood by non-epidemiologists. It's often expensive. It's unrepresentative of the real world. People make their own decisions. They don't just base what they do off what they've been assigned. And in that way, you might, if you're assigning some behavior even, or like exercise or something, like you're going to have people doing that wouldn't ordinarily, maybe, and in that way it's unrepresentative of the real world. You can still get confounding by chance with a low sample size. And yeah, I'm going to go over how to avoid that in another video. And also, there's a lot of things that are impossible or unethical to randomize. Like it's impossible to randomly assign race. You're born with that, and you can't assign someone a race they aren't already. Also, it might be unethical to randomize and assign harmful things like smoking. Luckily, people are kind of dumb and will self-assign themselves to all kinds of poisonous crap. So like you can just kind of use the fact that they're going to do it anyway and study that. But you can't randomize someone to smoke. You can't force them to smoke. So just some very final notes. I guess this is in line with the representativeness, where concept of like efficacy is in like very controlled, sterile settings versus effectiveness in the real world. Observational studies are more of an effectiveness kind of thing, while randomized control trials are more of like a sterile and unrealistic environment. Long-term studies are something that is often lacking, just because like to get a drug on the shelf, big pharma does randomized control trials that only like follow someone for a little while rather than following them for like several decades. So typically randomized control trials are followed up with long-term observational studies. And lastly, the people who volunteer to be part of a randomized control trial might be different than the general population, and that's something to watch out for.